Okay, can you hear me?
Yes.
Okay. Hello everyone. My name is Gabriel Rabanal Bolaños, and I'm going to talk about the cosmic results with the final micromega sectors for the Atlas Muon upgrade. So this is the outline of this talk. I'm going to talk about the NuSmell wheel, the cosmic array test stand, and everything we measure with it. So on slide 3, upgrading the Atlas Muon detector. So as you heard during the previous talk, the end cap detectors of the Atlas Muon spectrometer will be upgraded. And the places where the end caps are shown here in red. As you can see, we have side A and side C. The upgrade is not needed for the upcoming run 3 of the LHC, but will be needed for the high luminosity LHC. According to the NuSmell wheel technical design report, the TDR, the NuSmell wheel is expected to work at up to 15 kilohertz per square centimeter at a pseudo rapidity of 2.7. And a spatial resolution of 100 microns or better is needed for a momentum resolution better than 10% at 1 TeV, which is the resolution of the current small wheel. And you can see in the bottom right side how we need different sizes of detector chambers for overlap. These are called small modules and large modules, SM and LM. Now on the next slide, slide 4, we have the tracking technology of the NuSmell wheel. So the previous talk was about the triggering chambers, so this is about the tracking. So this is a comparison of the tracking technologies of the small wheel at the left and the NuSmell wheel at the right. So on the left side, you can see there's a cross-section of the monitor drift tubes, MDTs, which are still used in the rest of the Muon spectrometer. And on the right side, there's a cross-section of the micromegas detector, MM. So the micromegas detector is has a planar cathode, and then a thin metallic micromesh. And the gas between these two works as an ionization region because there's a gas here. The gas is a mixture of argon and carbon dioxide. And the electric field here drifts the electrons towards the mesh. And then this region here is the amplification gap, where we have the avalanche. So when a muon passes through, you can see there's ionization and then an avalanche here. And here we have the readout electrodes. So the electric field here in the amplification region is about 10 times stronger than in the drift gap. So the comparison is like this. So for the MDTs, the tube diameter is 2 centimeters, but for the micromegas, the strip pitch is 400 microns and the strip width is 300 microns. So we have smaller numbers here. This allows us to have better resolution. The maximum drift time of the MDTs is 700 nanoseconds, whereas for the micromegas, it's in the order of 100 nanoseconds. And the MDTs are used for precision tracking, and the micromegas is used for precision tracking, but also as a trigger. So in addition to the STGCs that were discussed in the previous talk. So in the next slide, we have the goals of the cosmic ray test stand that we have at CERN. So complete the final electronics integration of each micromegas double wedge or chamber, which looks like a pie slice. Test the data acquisition system, measure noise rate, high voltage, gas leaks, spark rate, sample the efficiency, get a sense of the resolution as well, and test a real detector with real muons. So on slide 6, we have this is a cross-section of a NuSmell wheel chamber with a muon passing through the NuSmell wheel here, through the trigger chambers in orange, and then the micromegas layers in green, which is the topic of this talk. On the right side, we have the different types of micromegas layers with the orientations of the strips in red here. So we have the so-called eta layers that measure the precision coordinate in eta, the pseudo rapidity, and also these other stereo layers that are tilted 1.5 degrees with respect to the eta layers to gather phi information. So on slide 7, we have the cosmic ray test stand at CERN. So 7 out of 16 small chambers, SM, were tested with cosmic muons with no minimum muon momentum. Each small chamber consists of 2 modules, SM1 and SM2, that are also shown below. And we have pairs of scintillators above that make a trigger with a frequency of about 100 hertz and partially cover the chamber below. So you can see here on the left a side view of the cosmic ray test stand with the scintillators on top that we use for triggering on cosmic muons and the chamber below. And on the right side, there's a bird's eye view. So a view from above with the chamber here in green and the scintillators above it. It's worth noting that the scintillators do not cover the chamber uniformly. So they cover mostly the central part, and this will be seen later today. So our setup is not optimal for measuring high momentum muons due to the absence of an absorber and scintillators below the chamber. So in the next slide, slide 8, we have the baseline electronic noise. So on the left side, there's an event display. The axes are not at scale. So we can see a cosmic particle creating a track by inducing charge in 8 layers. So this red line is a reconstructed track, but also there's noise hits in different layers, as you can see here. So the first thing we do is to measure the noise. So on the right-hand side, there's an example of a baseline noise per strip measured in one front-end board, which you can see here, strip number in the x-axis, and here baseline noise. This is for 100 measurements, and from this we can get the spread, the root mean squared, which is about 2.5 millivolts. And this RMS, this unit of the spread of the noise, is used to set up the signal threshold. RMS, RMS times 2, RMS times 3, etc. Because this changes from strip to strip. Once we measure the noise, then we can set up the strip threshold to decide when we get a signal. So, but first we have to try different thresholds to see how everything goes. So in order to trigger a noise, we delay the single signal from one scintillator. So we delay to avoid cosmic muons, and this is our trigger. So the hardware threshold that we set must be selected first low enough to get a signal, but also high enough to keep the noise below the predicted hit rate at a high Lumi LHC, which is 1 kilohertz per strip. So on the right side, we have the electronic noise versus hardware threshold measured in units of baseline RMS. And the noise rate falls as a function of the threshold. Given that we want our noise rate to be lower than the high luminosity LHC rate, we have to sit below this red line. And right now we are testing this setup, which is RMS times 9. And the effective charge threshold is 2.5 femtocoulombs. So this is an approximation of our current charge threshold per strip. So now that we set up the threshold, we can read our cosmic tracks, and we can see plots like this. This is a plot of cluster charge. So first, we have a simple clustering algorithm known as Pac-Man that is used to group neighboring strips into clusters that are used to find tracks. But due to the high strip threshold that we have to set in order to have low noise, then we get single strip clusters, as you can see in this arrow pointing to this peak here. Also, you can see the way the place where it starts to rise, which is the threshold at about 2.5 femtocoulombs, which is expected. And also for straight down tracks, we expect on average 3 strip clusters. So what this means? This means that these single strip clusters are because we're not getting all the charge from a cosmic particle because we're setting such a high threshold. But they do have an important contribution to the overall tracking and efficiency calculation. So we cannot get rid of them. So we have to use them also. So on slide 11, we have tracks, which are the physics objects. On the left, you can see, again, another example of a track going through the 8 layers. And on the right side, we have a track map of one layer, 1 micromegas layer that we make when you consider all the points crossed by tracks that are reconstructed with at least 5 layers. The main point of this plot is to show that our data is biased towards the center of the chamber because of the scintillator acceptance. On slide 12, this is a summary of the high voltage configuration. Each micromegas layer has 16 high voltage sections, as you can see in this picture, 16 pieces. So the TDR had 600 volts as the nominal high voltage, but due to sparking, the new nominal high voltage was set to 570 volts for the amplification gap. So, and if a high voltage section sparks at a high rate, then its voltage is lowered and lowered or turned off. So here on the left side, we can see an example of a possible configuration with one high voltage section at 550 volts, for instance, in orange, and everything else good. And for 7 small chambers tested in the cosmic ray test stand, roughly 89.6% are at nominal high voltage. This is fine, because even if we have sections that are not at nominal high voltage, we have 8 layers, right? So if one small section does not work properly, we have other 7 remaining layers that allow us to reconstruct a track. So this is fine. This is workable. So on slide 13, how we measure the efficiency with a tag and probe approach. So first, we exclude the layer I, we blind it, then we fit a line using the remaining 7 layers. If a track is found, this is a tag. And then we unblind this layer, and if a cluster is found within a window of the track projection, then this cluster is a probe. The allowed window is 5 millimeters for ETA layers and 10 millimeters for stereo layers. And the efficiency is just the number of probes divided by the number of stacks, which is a counting process. On slide 14, we have the efficiency. So here's an example of a micromega's efficiency map for a layer at nominal high voltage, which is 570 volts. On the left, we have a two-dimensional plot where you can see the efficiency in the fiducial region of 1 micromegas layer, with red equals an efficiency of 0 and green an efficiency of 1. And on the right side, we see the same layer, but this is the same layer, but this is just a 1D projection. So the same x-axis, which shows the efficiencies and the error bars. So here the axis is different. The axis is from 0.9 to 1, so we can see better the error bars in the data. So now this, so since this is just for one micromegas layer with good high voltage, then we have to study how the efficiency changes when we have lower voltages because we have sparking and we have to lower the high voltage. So we make high voltage studies, which is this. So this is a plot of a micromega's efficiency versus amplification voltage, high voltage, for small chambers tested with cosmic muons. So we have many lines in this plot, and this is because these are the results of various layers that could all hold nominal high voltage without sparking. This allowed us to lower or raise the high voltage at will, and this gives us a sense of the dependence of the efficiency of a good layer as a function of a high voltage. So at the very bottom in blue, we have the percentage of high voltage sections that are at each high voltage configuration for the 7 small chambers that have been tested so far. So here we can see 89.6% are 70 volts, which have like a nominal efficiency of about 94 to 96%. But even if you lower it up to like 550, then efficiency is about 80% or more. And sorry again. So I want to repeat again, this is not a problem. This is fine as long as the sections with low high voltage do not overlap on top of each other. Because remember, we have 8 layers. So if one high voltage section has low voltage or is turned off due to sparking, we have 7 remaining layers that do the tracking. And we never have more than 2 high voltage sections turned off that are overlapping each other. And on slide 16, we have the residuals. So an unbiased residual is defined as the distance between the intersection of a track with a layer, but created by blinding that layer. So not looking at what any cluster in the layer, and then the centroid of the closest cluster in said layer, if any. So at the left-hand side, you see the plot that I showed earlier, showing how we blind one layer to find the track with the remaining layers. And then we find the residual of the cluster in this layer with respect to said track. And on the right-hand side, this is a sample of the distribution of all such residuals. But this is for tracks whose incident angles are less than 5 degrees. So this is mostly vertical tracks that go perpendicular to the chamber. So that we were testing. So it is centered at So it is centered at 0, and it has a Gaussian-like spread, which is expected from a tracking detector. And you can see a simple Gaussian fit in red. It is worth noting that the spread of this distribution is not only the resolution, but this also includes the effect of multiple scattering and extrapolation error. So the true resolution of the chambers are actually a work in progress and need further investigation. And finally, on slide 17, a complete electronics integration with the final chambers has been done with cosmic rays, and it works. 7 small chambers out of the 16 were tested with cosmic muons at CERN, and no large chambers were tested yet at CERN. We determined how many sections hold high voltage, and the efficiency of each layer was measured. And also the projected timeline for this, as per the latest NISMOBIL review meeting on July 20th, was that the commissioning of the NISMOBIL Site A is projected to finish by May 2021, and the NISMOBIL Site C by October 2021. Thank you very much for your attention.
Thank you. Question to Gabriel.